Yeah, good morning. I hope you can hear me. Good afternoon, also from my side. I will share this presentation with Ralf Bandorf. Um, we will talk on different subjects, and I will start with the first subject with a very brief introduction into the basics of sputtering. So Ralf has the power for the screen, and I will tell him when he has to change the slide. We start with some fundamentals, and I will briefly report on the first modification of sputtering, namely diode sputtering and its limitations. Next, please. So assume a situation where we have a solid state surface and we have a high energetic ion. It may come from an ion source or from a low pressure plasma, and with several hundreds of electron volts, this ion hits the solid surface. There are basically 5 types of interaction. The first is the cathode sputtering. So that means an atom of the target gets enough energy to overcome the surface binding energy and then is emitted into the space, and by this a thin film is created. The second type of interaction is secondary electron emission. In this case, the energy of the ion is spent to generate secondary electrons. If the ion energy gets very high, but this means above, let's say, 10 kilo electron volts, which cannot be reached in our normal sputtering processes, then the ions will be implanted. The so-called collision cascade will spread deep into the solid target. The ion may be reflected. This especially happens for glazing incidents. If the angle of incidence is very high, this cannot happen in magnetron sputtering. And finally, and this is the most important part and the part which is concerning us very much, is the heat generation due to lattice vibrations. So this is the majority of the energy of the ion, as we see later. Next, please. So if we talk about sputtering, we have to deal with two major definitions, and there are two numbers which are very important. Both are dimensions with numbers without dimensions. The first is the so-called sputter yield, Y. And the sputter yield is defined as the number of emitted atoms divided by the number of incident ions. And the second one is the secondary electron emission coefficient, and this is defined as number of emitted electrons divided by the number of incident ions. Why are these numbers so important? Well, the first one defines the speed which we can achieve in depositing a thin film. And the second one is very important in order to keep the plasma in operation, because if a target delivers not enough secondary electrons, then even not enough ions can be generated, and the plasma will just turn off. Next, please. We can say that the sputter yield is a function of various parameters. And the situation is rather complex. These are a lot of physics are here involved, but I want to show you just one very interesting situation which could be used in the future in order to get very high deposition rates in combination with the plasma. And we have already first experiments in this direction. Sputtering is a cold process. So the phase transition is from solid to gas and back to solid. While in evaporation, the phase transition is from solid via steam, vapor, and then the liquid phase is in between, and then the vapor, and then again solid. So that means the sputter yield is just defined by momentum transfer and not by temperature. That's why for target temperatures, which are very high, even the sputter yield remains constant. But then if you go up to about 0.8 of the melting temperature of a material, then you have a huge increase of the sputtering yield. And that's what we observed during my last days at Leibold. We did already such experiments, and we repeated such experiments, especially with SiO2 here in Fraunhofer IST, and the results were very encouraging. But unfortunately, of course, you have to sputter up because you are going close to the melting point, but then you have a combination of sputtering and evaporation. You use the high deposition rate of evaporation combined with the high thin film quality, which you can get by using a plasma. Next, please. The next, what may be important to understand thin film growth is the energy of the sputtered particles. It is not the case that the energy of the sputtered particles is dependent of the ion energy, as it's shown here in this slide. Even if you have very high ion energies up to 1000 evolt, you will get the same energy of the sputtered particles. The energy distribution, it's called a Thomson distribution, according to Thomson, who first reported on it in 1968 or so. And he has shown that the energy distribution of the sputtered particles is only dependent of the surface binding energy. So, and the maximum is half of the surface binding energy. So now we can look into tables and we look at different surface binding energies, and we see that in general we have between somewhat within 2 electron volts and 8 electron volts. That means sputtered particles have an energy mainly in the range of a few electron volts. And this is a factor of 10 times higher than evaporated particles. And this is the reason why sputtered films are much more dense than evaporated films. So far, some physics. Next, please. What else do we have? Yeah, this shows the sputtering yield dependent on the atomic number of a target. The projectile here in this case is 400 eV argon. And you see some periodicity, and you see that the sputter yields vary between 0.5 and 2.5 atoms per ion. Of course, they are getting higher, but this is the typical case what you have in a magnetron discharge, 400 electron volt argon. Next, please. Yeah, after this brief introduction, we will talk a little bit about diode sputtering. Based on the principles, here you see a simple sputter diode where you have a target mounted on a copper plate or a target body. As I said, you have to cool the target. In case of diode, you need a dark space shielding in order to concentrate the plasma in front of the target. And in the opposite of the target, you have the anode, which is normally in an industrial plant, it's on ground. And the voltage typically you have at the target is several thousands of volts, so it's very high due to the low or the high plasma impedance, and you can obtain very low currents. So that's the problem of diode sputtering. The pressure has to be rather high in the area of 10 to the minus 1 millibar, which means you have a rather low mean free path of the particles. We can estimate that the mean free path in this pressure range is only about 0.5 millimeters. On the other hand, you have a large distance in the range of 10 centimeters or so between the target as the source of sputtered particles and the substrate. So you can imagine that the sputtered particles on their way lose a lot of energy during this travel. The target diameter for round cathodes are 100 millimeters to 400 millimeters. Rectangular geometries are possible, of course. And if we take the numbers here, then for a 200 millimeter target, a typical current of 0.3 amps results. This is not very much. And so we can say that diode sputtering is a process with a very low productivity. But that's how all started after evaporation, and diode sputtering was very common until, let's say, the mid of the 70s of the last century. What are the limits? As I said, in many cases, deposition rates are not high enough for cost-effective industrial production of thin films. You have a high electron bombardment because you directly bombard the substrate, which is on anode potential, and this causes a very high thermal load to the substrate. It was not possible to coat temperature-sensitive substrates. Production of a CD or even polyester foils, polymers, was not possible at that time. As I said, you have a high pressure, substantial scattering of the atoms. If they reach the substrate, they are maybe thermalized. That means they condense with low energies, and the coating quality is often not so good. Next, please. Yeah, you could increase the pressure in order to get more ions, in order to increase the deposition rate. The sputter yield is given by physics. What you can do with your parameters, you can only try to increase the deposition rate. Even in magnetron sputtering, the sputter yield remains unchanged, but you get much more ions in the same time. So if you try to increase the pressure, the mean free path is reduced. That means you will not improve your coding. You even make it worse. You could increase the voltage by a factor of 10 or so. Then you could increase the sputter yield. But on the other hand, who wants to have a discharge with 10,000 volts? And on the other hand, if the electrons get too much energy, the probability for ionization is decreasing. That means faster electrons, they make less ions. That's the problem. As I said, diode sputtering found more or less its end in the mid of the 70s. And the problem was at that time, how can the dilemma be solved? And of course, the answer is you have to produce more ions, but not by increasing the pressure. You have to raise the degree of ionization, alpha of the plasma, but also you have to increase the mean free path of the sputtered material. That means simultaneously you have to reduce the working pressure in your discharge. And this was the coming up of the Magnetron cathode. And here I hand over to Ralf, who will continue.
Yeah, one approach in between from the diode to the magnetron is the hollow cathode. So we can also think about using a hollow cathode, a specific configuration of the sputtering source design, which will enhance the ionization and therefore produce more film-forming particles. But nevertheless, I need to also get the coating to the process, to the substrate. So in general, we will have a low pressure glow discharge with a hollow shaped cathode. This can be like a cup, hollow cathode, which I have where I apply some voltage and I ignite a glow discharge, and the electrons, of course, will be highly concentrated within the source. On the charge carrier losses are strongly reduced due to the chamber walls, because the electrons need to escape to reach somewhere the anode outside, and this allows for increasing the plasma density, and in the end we get a significantly higher current density and we end up with a process providing a very high plasma density. So if we consider an ordinary glow discharge, we have the negative area, the cathode fall, where we have our cathode on a given potential, and then we have the plasma potential positive, usually the most positive potential in the chamber, and then if we have a grounded anode, like Günter was mentioning before, we will have a drop, also a small drop towards our walls or to the substrate, which might be on the ground potential. If we have a hollow cathode, we just encapsulate the electrons in the middle and we capture the plasma, and it's rather improbable that we even reach such a high level. We will have different voltage, and especially we cannot allow the electrons, or we don't allow the electrons to escape and increase the plasma density in the process. So the one approach to get a high deposition is to drive out the sputtered particles in such a hollow arrangement, which could be a tube or it could be some parallel plates. And we have a laminar gas flow of argon going through the source, allowing for the sputtering, but also transporting the material towards our substrate. So we utilize the hollow cathode glow discharge. We are sputtering within the inner area of the cathode surface. And similar like in the diode, we have an almost full phase erosion of our target. So we have a high utilization of our target, and we propagate and move out the material by the gas flow, the flux itself from the argon. And then we can incorporate additional reactive gases outside the source. And this also has the benefit, if we do reactive sputtering, we even increase the rate. So if I do a titanium coating and I add oxygen, I increase the rate by the amount of oxygen I additionally add to form titania in this case. And there's a lot of flexibility also with this approach to synthesize coatings. Of course, you have the temperature, you have a biasing, you can attach an additional voltage to the substrate to define the morphology of your growing films. So some examples for films of columnar structure, you can find going to finer and finer columns in that area of different elements, zirconia, copper, alumina, titania, PCT, or even highly porous materials, which you can use as catalysts or for gas sensing, for example. But you also can do the opposite. You can go for very dense coatings, densification of the coating, in that case by additional applied bias towards the substrate. So we can tailor the properties of the films, we can tailor the microstructure of the films, and even going to really highly porous structures, also for example for thermal barrier, or when you want to intercalate some materials, like for example considering aspects of battery, where you want to allow for some expansion during a volume growth or volume modification in the films. And this will bring us back from some specific configuration of a diode-like type, because you don't need any magnets with the hollow cathode. If you set up the hollow cathode, that's also a very interesting approach, especially for magnetic material. You can have a high rate sputtering process for magnetic material because you don't short circuit your magnetron because there are no magnets involved up to this point. This brings us to the development and the quest how to move from the diode with the low rate to a higher rate, or reducing the working pressure, allowing for a longer free mean pass and therefore for higher energetic film deposition in that situation. So we are moving from the diode. So we have the diode that you've seen before, the schematic of the diode, and we add yoke, we add permanent magnets and a magnetic arrangement. This could look like you've seen here in a round magnetron, or you can have linear shaped magnetrons. There can be different design configuration of your sputtering sources that you can use and utilize. And the benefit you gain by this is that you capture your electrons in front of the target. You capture them in the magnetic field lines, and the electrons, and we will see later on a movie simulation from a colleague of ours, the electrons will oscillate between those turning points. They will pick up energy towards the middle, what's then later formed the racetrack in the target, and then be decelerated. And on top of that, they have a radial drift. And they, of course, will fulfill and follow the Lorentz equation, and will follow just the E cross B drift of your magnetic configuration. So this will look like, if you come here, having a model. So this is the model of the target with our magnetic configuration. And here you can see already the magnetic field lines. And the simulation shows us what's happening if we start the discharge, if we ignite our plasma. Let's see, the movie needs a short moment. So here we go. What you can see is the electrons, some of them can escape, but the others are captured on the field lines and they start oscillating and following the magnetic field lines in front of the target, increasing the electron density, increasing the plasma density finally, and this will lead to an enhanced sputtering yield and enhanced deposition rate for our coating. What's happening from a different perspective, you can see by this modification. So here the electron starts and the electron will propagate and will pick up energy, decelerate, increase, decelerate, while moving between the north and south pole of your magnetic bars. And they will have an orbit, they will propagate in front of your target, and then they will also move and follow around the length or the structure of your cathode. And so what's the big difference? In the diode, that's an example I'm given here for aluminum. In the diode, you are working at least one order of magnitude higher pressure, working pressure, because you need the higher pressure, you need a higher particle density to ignite the plasma, to get your current to sustain your discharge. And what you see is you have quite a low discharge current and you're operating at a high discharge voltage. With introducing the magnets for the magnetron, you can switch this behavior. You can lower your pressure and you end up with a significantly higher current at way lower discharge voltages in that. And this was realized, and I will hand this over to Günter again with different magnetrons and industrial designs for the cathodes.
Okay, should I continue already?
Yes.
Okay. Okay. Yeah, here you just briefly some industrial cathodes. Here you see on the left side, you look through a window in the side of the glass coder, and you see a 3,750 millimeter magnetron cathode for the deposition of thin films on the so-called jumbo-size glass substrates. I'm not sure if the dimensions are correct. At least there are more than 2 meters, 3 meters times 6 meters. On the left side, you see such a magnetron, and you see the characteristic racetrack. Next, please. Yeah, Magnetron sputtering, and even it was at the beginning of the 80s when the glass coders came up, and everyone wanted to have the new magnetrons. And here you see different kinds of magnetrons in a web coder, even for metallic sputtering or for reactive sputtering. In this case, it was ITO from the metallic target in a reactive process. Next, please. And here you see a magnetron cathode in a batch coder for tribological coatings, which we have here in the Fraunhofer IST. The cathodes are more than 1 meter in length. Yeah, so we had to face a lot of challenges, and the first challenge was the transition from the diode sputtering to the much more efficient magnetron. Then the second challenge was, of course, the target utilization, and it was a long way. And at that time, BOC coating technology in 1988 introduced the so-called rotatable magnetron, or CMAC, and everything was solved here, or seemed to be solved. There were some problems at the beginning, but today it's state of the art, and the idea is fantastic. you use a tube instead of a planar magnetron, and you rotate the tube around the plasma, and by this you can get around 90% of target utilization. You can enhance the lifetime, and you can also enhance, of course, your service intervals. Next, please. Yeah, today's standard, I said, here we have an old picture of BOC, and here we have already a dual magnetron for MF operation, for operation in the mid-frequency range. And you see the two target tubes, which are acting as cathode and anode and vice versa. And this today, I must say, is the state of the art in large area coding. So if you want to do something good, you change from DC to pulse. We have no time to talk about the benefits and disadvantages of RF sputtering, but now I want to move to pulsed magnetron sputtering. And pulsed plasmas are not so new, as you see. Even in the 1950s, they made first investigations on pulsed plasma processes for surface cleaning and modification. And then it was quiet a long time. And first significant patents for the deposition of thin films using pulsed magnetrons were filed in the late 1980s. And then three institutions started to work seriously on pulsed magnetron sputtering, namely the so-called, at that time in the GDR, the Institute von Ardenne, and in parallel the von Ardenne Anlagentechnik, at least in Germany. And in Hanau, I was involved very much in the development work of Leibold. And as I said, today pulsed magnetron sputtering is an established process in numerous production plants for various applications, and it will deliver the best film quality, but not the best, because the best film quality maybe is made by Ralf, by HIPIMS. But at that time, pulsed magnetron sputtering was a very big step. Next, please. So you must imagine, if we go back to the early 90s, I must say my professional life between 1985 and 1990 was mainly determined by arcing. And Frank knows this well. We had to develop deposition processes for the deposition of dielectric layers. And there was a big demand of making silicon nitride layers, titanium oxide layers, silicon oxide layers, silicon oxide in a large scale, and it was not possible. Why was it not possible? There were two main problems. If you try to deposit within a DC process an insulating material, after 1 or 2 hours, you will generate arcing. Why? You will coat, of course, you need for a DC process, you need a conductive target. That means we use silicon and we sputtered silicon in an argon oxygen gas mixture. And okay, it worked well in the beginning, and after 1 or 2 hours, all the inner surfaces, they were coated with the high insulating material, and there were huge potential differences, and this caused arcing. The other thing, and I remember the technical director of Advanced Energy at that time, it was Richard Scholl, and in the 90s, he created, I think, the term disappearing anode. The disappearing anode, that means if you have a clean anode in the beginning, because you have clean surfaces around the target, but with time, all inner surfaces are coated, and you have the disappearing anode. So the discharge will not stop, but the plasma will get unstable, and the frequency of arcing will dramatically increase. So it was not possible to get a stable process for a long time, and we were rather disappointed. Yeah, and then the idea of pulsing came. So at that time, the power supplies, they were only laid out for DC. No one had MF power supplies for such a high power we needed for the 3.75 m cathodes. You need up to 200 kilowatts of pulse power. So what can you do? The option one is you can use a unipolar rectangular pulse with one cathode. That could help a little bit, because an arc cannot develop over a long time because you switch off. What you see here is the big disadvantage: you lose deposition rate. Yeah. Then the option two was you use a bipolar rectangular pulse. That's how many single cathodes today are still driven. You switch to positive, and then you can support the discharging of the surface. But even you lose rate, and the best option is you use two cathodes. Next, please. Yeah, you could use a bipolar rectangular pulse, or you could use a sine wave. And at that time, we started at Leibold with a power supply with a sine wave, which we got from a small German company. And what was generated, next please, was what we call the twin Mac. And this is now, as I said, an example how you very much can improve your process, the stability of your process, without losing any deposition rate. So the idea was take two cathodes instead of one. You completely decouple it from the rest of the machine. So no matter if the rest of the machine is coated by an insulating coating or not, the two electrodes, I must say, they do not bother about this. We worked at 40 kilohertz. The frequency is not so critical. Today you can work at 10 to 100 kilohertz, and you get a huge variety of power supplies for this frequency regime. So in the first half wave, the left electrode is acting as the cathode, and the right one is collecting the electrons as an anode. And charge is having built up. Pardon?
Here we mix the signs. This must be plus, and this must be
yeah,
minus.
I see. Yeah, I see. Sorry. Of course, in the right part, the left one is the cathode, and the right one is the left one is the anode, and the right one is the cathode. So you switch just the plasma between these two electrodes, and this turned out to be very successful. Why? Next, please. You have the medium frequency excitation. That means you could eliminate arcing, and you have two cathodes. That means you use a high electron flow for the reduction of charges, and you have what we then called an ever clean anode. So that was the idea, and you will see later in the simulation and in the real result that it was really the right idea. So what we got was a high deposition rate. The physics were not changed. The sputter yield remains the same, unchanged, because the sputter yield is only determined by physics, but you could apply a very much higher power, and by this you got a higher deposition rate than for conventional DC sputtering, up to 10 times higher for small cathodes, and a stable long-term operation for the complete lifetime of a target was demonstrated at that time. Next, please. Yeah, here you see now, this is a picture of Fraunhofer FEP, how it works. In the first half wave, we have the sputter cathode on the left, and you see how the glow is moving to the anode. And then we switch in the second half wave, and it's vice versa. And our group around Andreas Flug has simulated this. And you see here the simulation. Yeah, that was a very important development, I must say. And during the 90s, this development spread more and more in industry. And for the deposition of dielectric films on each size, today I still would recommend the mid-frequency sputtering or pulsed magnetron sputtering using a dual cathode arrangement. Here you see some deposition rates which were obtained for silicon dioxide. We compare a mid-frequency dual magnetron with 750 millimeter length with a single magnetron of 3,750 and a dual magnetron of 3,000 millimeter. You see the deposition rates are a factor 2 to 5 higher than in the DC sputtering. So we looked at film properties. Next, please. And we were again very much surprised because we had much better film properties in MF case than in DC case. And we didn't understand this in the beginning, but later on, we had a colleague here, Bernd Süsker, and he was the first who measured ion densities and ion flux at the substrate for these MF process. And of course, if you have the anode, then the electrons are moved towards the substrate by the electric field. So in case of MF sputtering, you have a much higher bombardment of the substrate than in case of DC sputtering, and this acts like a bias you apply often. Yeah, and you see in case of MF, we have a higher density here in case of the silicon nitride films. Of course, and this is always the case, the density decreases with the argon pressure. That's well known, but you see a higher density, and even in case of the hardness, next please, you see that the MF sputtered films are much harder. So this is these are only 2 examples out of a student work we did at that time. You can do this for silicon dioxide. We did it for titanium dioxide. We got a very dense structure in case of titanium dioxide, and even for tin oxide. So you can use every material, and you see that the properties are much improved in case of MF sputtering. Have I another one?
And in this case, with the sputtering, okay, of course, you can apply for the mid-frequency. You can, like Günter mentioned, have a sine wave, or you can have the rectangular shape of the sputtering cathode. In the rectangular shape, you can allow for even adding some positive, some bipolar sputtering, some positive overshoot to decharge your cathode, mainly for the single cathodes. And if you increase or further stretch the approach of the pulsing, then you come to the high power impulse magnetron sputtering. So the main idea is, what we know already is, in the conventional sputtering, we are operating mainly with neutral particles. The fraction of ionized film forming species is a few percent at maximum, depending on the material. If you go to the pulse sputtering, you increase the plasma density, you have with the pulsing and switching of the pulsing, some hot electrons, a lot of plasma physics, and in the end you end up with some higher energetic particles, what Günter mentioned, also leading to denser films, to harder films, and depending on the shape what you have. And if you want to go further, then you can go to HIPIMS. That means you have a DC-like discharge or pulse discharge, and you squeeze with the same average power the whole discharge in a very short period of time of a pulse. And by that, the power delivered to the cathode in the pulse will have a few orders of magnitude higher power or current than in the continuous DC case. And this will lead to not only influence of a lot of neutral particles involved, but you will switch to mainly sputtering with a significant portion of ions, and also the film structure is expected to change even more dramatic. So there are a few aspects on this. So if you have charged particles, if the film forming species themselves are charged, you can guide them in electric and magnetic fields. So you can even use them to filter or to accelerate, decelerate, to use additional configurations to play around, or to also guide them around some corners. You can guide them cleverly to reduce or avoid sidewall deposition. You get a more conformal coating even for complex shaped surfaces, or even if you're facing a surface which is perpendicular to your target, you still can grow, if the ionization is high enough, a film perpendicular to your substrate, even though it's 90 degrees towards your target. We had nice results, and there's some papers available where you can see that if you grow under a tilted angle, that for keeping this tilted angle but increasing the ion flux or ionization of the process, you will just lift your growth direction. And if you have some columns you can see, you will end up in growing a film perpendicular to your substrate. Of course, the ionization depends on the material you're looking into. So carbon has a quite low sputter yield, and also a low probability for ionization. So you need a lot of energy for ionization. But there are other elements where you can create a significant higher fraction of ionized flux. And there were two definitions given for HIPIMS in that case. So you can go or follow a technical definition and say a HIPIMS is a kind of pulse sputtering where the peak power exceeds the average power by typically 2 orders of magnitude. So this implies that you have a long off time between your pulses, and this also then will result in impulse sputtering. Or you can come to the physics and you say the HIPIMS is a pulse sputtering where you create a significant fraction of sputtered atoms that are ionized. So the film is mainly formed by ionized species, or significantly increased amount of ions forming the film. This implies that also effects like self-sputtering can occur, which can just subside the sputtering process from the gas, and you can have also sputtering by the target material itself. Some description on this is given by the pathway model. This was proposed by Dave Christie and improved by Jaroslav Wilczek. And we look at our substrate we want to coat and our target. And we start with an argon ion, sputtering the target with a sputter yield for the argon hitting the target and releasing some target material. So the sputter yield for a gas ion releasing a target material. And we have a neutral target atom, and there is some probability that this can become ionized. You have a target ion, and this again can be back attracted to the negative target and can sputter again with a sputter yield that I release a target atom by sputtering with a target ion. Of course, I can also just have the neutral particle leaving the target, and even in the bulk plasma, there is some probability that by collisions this can become ionized and then reach as an ion the substrate. So we can form the ions here, and we can grow a film with ions, or we can lose some of the species. Same also for the neutral particles, we can lose some or we can form the film, and the amount of ions significantly is increased in the HIPIMS process. So just some small animation for this. You can find it also on the web from the cost action. I think I removed the sound, but anyways, so you have a sputtering chamber, you have a normal sputtering plant, and like I said, you take the DC discharge and you squeeze it in a short pulse, and that means you end up with a high peak power during the single pulse. And this will result in a different morphology. In the DC case, there might be some disorder, there might be some dislocation and some voids. And in HIPIMS, you can end up with really dense films. That's an example for nichrome coating. Or if you go to even very fine structures, you can coat the walls and side walls of very tiny features. Here, that's something with a diameter in the range of a few hundred nanometers and a micron in depth, can be even higher. And today, you have a lot of sputtering machines. So this just a view in our one of our coding labs, where you have today those processes in industrial production. So what we wanted to use as a kickoff for any discussions, and from the different aspects, you already can assume there is no easy answer to the question whether you use DC, pulse DC, mid-frequency sine wave, whether you use HIPIMS, whether you use RF, which is in some cases similar to what you have with mid-frequency. You will have even more, a bit more higher plasma density. You also have the chance to sputter insulating materials due to the nature of the process, but we decided to not go into details here. And it depends on the application. So you have a slew of technologies and approaches you can use. So the question we started off, we also want to close this. So what to choose? So maybe let's start with some aspects to consider. What does your coding system look like? Do you have an inline system? Have you a cluster machine, a batch coder? What's your environment you're dealing? Do you have access to just a single cathode? Do you have two or more cathodes, one, two chambers? This will allow you whether you have single operation, unipolar pulsing, whether you can go for dual configuration, and so on. If you sort out this one, what comes next? What material are you interested? Is it metallic? Is it insulating material? What kind of material you're focusing on? What's your application? What's your market segment you are aiming to, where you're shooting at? What's your product? What's the value you add to a product with your coding? And so what are the main drivers for your process? Is it the productivity, the cost of your process? Do you need a fast throughput? And you maybe can have some trade-off in the film quality, but you need a higher film thickness, or you just need some kind of film in a short period of time. Or can you allow to a very slow growth, but a very high quality of your film you are looking into? So these are all parameters you should consider, bearing in mind all the different configuration, all the different forms you can have with your sputtering cathodes that you can address. So we would like to end with giving this insight and some framework, some boundary on the sputtering And now let's go into discussion of your individual challenge and to look whether there are specific aspects and approaches and ideas where we could cancel out some options, or we can point out towards some direction where to go. And thank you for attending and looking forward to really interesting discussions.